today's Foxconn Quantum Computing Seminar. We have the pleasure of having Joel Rajakumar. I hope I pronounced that correctly.
Yeah.
So he is a PhD student at the University of Maryland, specifically at the Joint Quantum Center there. And he is advised by Dr. Yi-Kai Liu. And his interest is broadly on quantum complexity theory and error correction. And currently he's working on trying to pin down the computational power of noisy quantum devices. Okay, so Joel, if you please.
Yep. Thank you for the introduction. So yeah, let me share my screen. Are you able to see this?
Yeah.
Cool. Yeah, so today I'll be talking about our recent result, a polynomial time classical simulation of noisy IQP circuits with constant depth. This is joint work with James Watson and Yi-Kai Liu at the University of Maryland. So I'll get started. So to set the scene for what this result is broadly about, it's in the context of quantum supremacy experiments. So what these are they're tasks that are expected to be difficult for a classical computer to solve. And you hope that these are tractable for a near-term quantum computer. So those are like kind of the two main things. It's difficult for a classical computer, and hopefully you can implement this on a near-term quantum computer. This is the setting, and some of these examples of these circuits are random circuit sampling, and this was implemented by Google recently. Well, not recently now, but some time ago. IQP circuit sampling, which was implemented recently, and boson sampling. So these are all just examples of this broad task of quantum supremacy experiments where you're trying to find a problem that's difficult for a classical computer to solve, but you can implement in the near term on a quantum computer. Now, another...
Can I just ask, ask quickly something?
Yeah, sure.
How do we know that these are indeed problems that are difficult for a classical computer to solve?
So I guess I'll be getting to that. So usually you try to have some sort of complexity theoretic evidence. So you try to make some sort of argument where you reduce the problem that the quantum computer is solving to some sort of problem that is usually outside like the polynomial hierarchy, or like something that if it were classically simulatable, it would break some complexity theoretic assumption.
Okay, yeah. Okay, maybe I was getting ahead of myself.
Yeah.
Yeah.
I'll kind of get to that later on, but yeah. So another hope is that these tasks are efficiently verifiable as well, but I won't be touching on that in this talk. So the main thing is you hope it's difficult for a classical computer to solve and tractable for a near-term quantum computer. And those are the two things I'll be concentrating here, is whether we can find a problem that does both. Now, one candidate problem that people talk about, as I listed, was the IQP circuit. And these are conjectured to be hard to sample from. And this is sort of what I guess you were asking, is that, yeah, so I'll get to that in a sec. But just to explain what an IQP circuit is you start with every qubit in the plus state. So this is a 0 plus a uniform superposition of 0 and 1. And you apply a unitary D, which is 1. It's diagonal in the computational basis. And 2, you use a gate set, such as TCS, CZ, CZ, CCZ, RZ, or rotations. These are example gate sets, but like the main thing is that you can construct a circuit that generates this diagonal unitary. And the circuit is composed of some fixed gate set, such as TCCS, or these ones listed. Now, finally, you measure in the Hadamard basis. So, so the motivation for, actually I have a diagram here. Yeah, so that's a diagram of what the circuit looks like. And there's a couple motivations for this. And one, there is evidence that this is hard to exactly sample from the output distribution after a constant depth. So that is, hard means it is, if a classical computer were to be able to sample exactly from this output distribution, it would break some sort of complexity theoretic assumption. the particular assumption here is the polynomial hierarchy does not collapse, which is basically a complexity theoretic way of saying, like, it's a slightly weaker, sorry, it's an assumption that's similar to P not being equal to NP. It's one of those complexity theoretic assumptions that we assume is true, and we use it as a tool to make hardness proofs. So now, another thing that was proved after that is that it's hard to approximately sample from these output distributions in the average case. And again, this requires a couple complexity theoretic assumptions and some conditions as well, something called anti-concentration, which I will get into later. And the other main motivation for using an IQP circuit is that this does not require a universal gate set. So if you can prepare your qubits in the plus state, and if you can measure in the Hadamard basis, the actual circuit that you can construct, that you need to construct, does not require a universal gate set. It requires just these diagonal gates. And hopefully it's clear that this doesn't generate the full unitary group. It just generates like a diagonal, these diagonal unitaries. So these are the IQP circuits, and this is sort of the state-of-the-art hardness. Do you have any questions?
No, I mean, I'm just thinking, like, based on the gates, not even just diagonal. So there's basically, like, it's a unitary with phases on the diagonal. And I think the phases are not even, like, it's not even everything is possible, right? There's only a few possibilities.
Yes, yeah. So since this is a discrete group,
like you're not using an irrational phase angle somewhere, so it would not. Okay.
Yeah. So I guess yes, you don't need it to be any possible diagonal gate, but some discrete.
But still, it's enough for what we want.
Exactly. Yeah.
And okay, just to clarify, depth 4 means I have these unitaries 4 times.
So that means I can construct a unitary, this D, with a depth of 4 of.
Oh, okay. Like in terms of the gates.
Yeah.
Yes.
And usually we're talking about 2 qubit gates. So depth 4 is like 2 qubit gates. So now at the same time, there's some results about the easiness of these circuits when they're under noise. So practical implementations of these quantum supremacy experiments, whether you use IQP or not, are going to be noisy. So this is sort of the diagram we're going to be using is in between every gate you apply, you expect to see some sort of noise channel being applied by the environment, essentially. Now, one of the existing results is that noisy IQP circuit output distributions can be approximately sampled from in quasi-polynomial time, assuming anti-concentration. And I mentioned anti-concentration before as an assumption that gets you hardness. It turns out that it also gets you this sensitivity to noise. So the same property now makes it so that you can classically simulate it, quasi-polynomially with this assumption for this particular class of circuits. Now, this proof technique, it's a pretty interesting technique, and it's been used in a couple other results. It's also been used for random quantum circuits. This is pretty recent. Again, you have to assume this anti-concentration property. But this is just sort of to broadly talk about, like, when you add noise into the circuit, these hardness assumptions don't necessarily hold anymore, and it starts to become a little bit more subtle. Sometimes classical simulation algorithms can take advantage of this noise, and simulate these circuits. So now we can kind of state the broad question we're going to try to answer, is under what conditions can we classically simulate IQP circuits with uncorrected noise? So if you noticed in all these circuits, we're introducing noise in between the gates, but we're not doing intermediate measurement or introducing fresh qubits. So if you look back at this diagram again, I'm just letting my circuit go with the noise interspersed. And I'm hoping that it's still hard to simulate. But basically now we'd like to answer, is it hard to simulate? Can we classically simulate this into some conditions? So this is important for a couple of reasons. Firstly, it lets us assess current experiments. So are the near-term quantum supremacy experiments, the ones that we're hoping to implement in the next few years, are they actually infeasible to simulate classically? Or are there going to be classical simulation algorithms that will be able to spoof these? The other goal is that by actually understanding these conditions that allow classical simulatability, you can hope that you can guide future experiments. So you can actually pinpoint, the goal is that you'd be able to figure out what aspects of the practical implementation make the task easy, and therefore also what aspects might make it hard. So in this case, for example, we're taking uncorrected noise, right? We're using local gates. We're not allowing adaptive measurement. And we're able to see classical simulatability. And when you remove some of these conditions, maybe it sort of gives you hope for when it might not be classically simulatable. It sort of delineates that area, the sort of conditions where you might need to make an experiment that is hard to classically simulate. So now let me state our main result. We provide a polynomial time classical simulation algorithm for sampling from the output distribution of any IQP circuit beyond an O of 1 depth when polynoise, and this is independent single qubit polynoise, of constant strength is interspersed between gates. So the important thing here is this does not require anti-concentration. So I've shown before that there are results that already show this sort of sensitivity of IQP circuits to noise, but these require this assumption of anti-concentration. This actually works a little bit more generally for any IQP circuit. So now to sort of place this in the context of other results, as you increase the circuit depth, it's already understood that your noise will build up. And we know already that when you go beyond a log n depth, you should be classically simulatable because your output distribution is essentially completely random. So this is if you go up to, like, if you go beyond a log n depth. Now, it's also known, and this is the result I was talking about with anti-concentration. This is a Bremner, Montanaro, Shepard, that in the average case, assuming anti-concentration, you again see simulatability. Their particular class of circuits required O of log n depth. Our results show that you actually see simulatability at omega 1 depth without using an average case assumption or without using anti-concentration. So again, just to like hammer home this generality, because that's kind of the interesting thing here, is it applies to arbitrary circuits, including all-to-all connectivity. So you don't have to assume 2D or some sort of like bounded degree architecture. And you practically you'd actually see that simulation becomes easier when the connectivity is constrained. And it applies to generic polynoise channels of this particular form. Just to parse this for you, a polynoise channel applies an X error, a Y error, or a Z error with certain probabilities. This applies to any polynoise channel as long as it doesn't only apply an X channel, and that's this NP00 over here, or it doesn't only apply a Y channel. So essentially, it needs to have some sort of Z component or combination of X and Y components. This will be clearer as I go why this is so. This is sort of an artifact of the way we prove this. Essentially, we are using the Z errors primarily in order to get simulatability. And finally, it applies to any diagonal gate set where gates act on O of 1 qubits. So I mentioned a couple canonical gate sets earlier, but this is actually general to any gate set as long as it's bounded locality. So again, it does not require anti-concentration. So just to go in, zoom in on anti-concentration a little bit, it's something that comes up in proofs of hardness and easiness, as I mentioned, and it loosely captures how you converge to the uniform distribution. And it requires your gates to be randomly sampled. And so this is sort of the equation for anti-concentration, but I won't get into that. So I'm going to go into the proof. I will sketch out the proof for you right now. But before that, I'll stop in case anyone has any quick questions about the sort of what the context of the result is. Okay.
Yeah. So
I guess.
Yeah, I can hear you.
Me first. Okay. So you say you must exclude the poly channels. I mean, your poly channel must have some poly Z noise, right, to make it work. So you said
yes, yeah, some poly Z noise or both X and Y.
Like
yeah.
Is this because you are like using like a computational basis, the unitary which is diagonal in the computational basis. Is this related to this reason?
Exactly. Yes. It'll probably be clearer why later on as I go through the proof, but that's exactly why. It's because we're diagonal in the computational basis. So the z component is what you can sort of commute through these gates.
So is this constraint can be relaxed, or like when you apply the unitary, can you just change the basis and get other result?
So I believe you can. So for example, if you like did an IQP circuit in a different basis, that is, you prepared in a different basis and you measured in a different basis as well, then yes, you'd be able to find a different basis for your polynoise channels that would allow classical simulatability. But you would still have some component missing, like that is in your different basis IQP circuit, there would be some poly channel that this proof does not handle. Does that make sense?
Yeah, that makes sense. I'm just wondering, can we just apply the more like gates, which are not just diagonal? It's
So if you apply gates that are not just diagonal in some basis, then it leaves the IQP framework. It's not an IQP circuit anymore.
okay. So your motivation is that even IQP setting is easy to simulate. So if it's beyond IQP, probably it's hard to simulate.
Yes, yeah, that's sort of this kind of a final point we'll get to is that yes, if you leave the IQP framework, this doesn't work anymore. So yeah.
Okay, that makes sense. Thank you.
Yep.
I just have a short question, actually.
Yeah.
You mentioned that you're going to talk a little bit more about anti-concentration, right? Are you going to give more of intuition later on?
No, this is sort of it. So yeah.
So could you expand a little bit about it, and also tell, like, you said a few times that it's important that you're not using it. So why is this important?
Okay, so I guess anti-concentration requires you to, I guess the main thing is you require your gates to be randomly sampled. So it's not a sort of statement about any circuit. It tells you that in the average case, you are classically simulatable. And this is sort of important because maybe if you were trying to generate like a hard to sample circuit, you might say, okay, I'm not going to choose my gates randomly. I'm going to choose them in a clever way that avoids the noise. So this is an important result because since you don't require anti-concentration, doesn't require gates to be randomly sampled, it's stronger in that it works for any circuit, even the worst case circuit. The reason why I'm highlighting the anti-concentration thing is because it's like a proof technique that keeps coming up in these classical simulation literature. For random quantum circuits and for IQP circuits, all of the existing classical simulation results for polynomial time kind of require anti-concentration. So it's interesting that we're able to see simulation without requiring this tool, basically.
Oh, I see. Okay, thank you.
Yeah. I guess one more thing just conceptually is that anti-concentration is capturing a convergence to the uniform, and the output distribution of this IQP circuit could be very peaked. And people have talked about like the hardness of peaked circuits and like verifying peaked circuits. And this is sort of saying that even if it's peaked, it's classically simulatable. And that's maybe interesting for other reasons.
But if it has an output that is peaked, then it's going to be harder for classical circuits to simulate it? Like, do we have those results?
We don't have those results, no. But yeah, it's just something that I think people have talked about, is that the anti-concentrated regime is something that people have studied. So now there's a regime of, okay, if you have slightly peaked circuits, are they hard to simulate? there's no positive results there. This is giving a negative result there.
Okay. Okay. Thanks.
Yeah. So so I'm going to outline the proof here a bit. We're going to work through an example case. So we're going to take a circuit constructed from this particular gate set, T and CS, and we're going to choose interspersed dephasing noise. So this is only the Z component, only Z errors. And there's 3 steps broadly. We're going to replace entangling gates with classical gates using noise, induce percolation, then we're going to see a phase transition. These are just the headings. I'm going to explain each of one of these steps in its different slides. So first, we're going to replace entangling gates with classical gates using noise. So the first fact we use is that dephasing noise, Z errors, commutes with diagonal gates. So if you have a circuit, an IQP circuit interspersed with Z errors, you can commute all of these Z errors to the beginning of the circuit, and they build up in your depth. So this is sort of seen in this diagram. You have a bunch of noise on one qubit. You can commute it through the gates, and it builds up at the beginning of your circuit. Now, the second fact we use is that dephasing noise acts in a very predictable way on the plus state. It replaces the plus state with the maximally mixed state, which is a mixture of 0 and 1 state. And this is sort of subtle. It's a little trick we're kind of using here, is that normally when you think of dephasing noise, you think of it as applying a Z error with some probability. So then you'd say, I have a plus state with some probability and a minus state. That's what the Z error would convert it to, with some probability. But instead of sampling the noise like that, we're going to sample it as a mixture of the plus state and the maximally mixed state. And these mixtures are actually the same. You can represent it as a mixture of plus and minus, or you can represent it as a mixture of plus and maximally mixed. These are equivalent mixtures. So this is sort of shown in this diagram. When you dephase your qubit, you're taking it closer to the center of the Bloch sphere, which is the maximally mixed state. And then this maximally mixed state can be represented as a mixture of the 0 and the 1 state. So really, every time an error happens, we collapse here. So with certain probability you remain in the plus state, certain probability you go to the maximally mixed state. And then this maximally mixed state we're going to represent as a 0 or a 1. So in the circuit diagram, I have my noise concentrated on, say, on one of the qubits. Now, when the noise, I'm going to sample from the noise. It's either going to leave the plus state unchanged with some probability, or with some other probability, it's going to replace it with the maximally mixed state. This maximally mixed state I can replace by sampling 0 or 1 with equal probability. So my errored qubit gets replaced with a 0 or a 1 with equal probability. Now, the next fact we're going to use is that diagonal gates act classically on computational basis states. So the T gate acting on a 0 or a 1 introduces a global phase, which can be ignored. And the CS gate becomes a classically controlled S gate. It doesn't introduce entanglement. To sort of see this, once I sample a 0 or a 1 on my errored qubit, now my CS gate is a classically controlled gate. If it is a 0, it does nothing. If I've sampled a 1, it applies an S gate in the rest of the circuit. So to sort of see why it's not doing entanglement, it's a classical correlation, not a quantum, like it's not entanglement. Based on whatever I sample, a 0 or a 1, I've changed the rest of my circuit, but there's no entanglement going to be left between my classical qubit, that is like my qubit that's in a 0 or 1 state, and the rest of the circuit. So maybe you can sort of see where I'm going to go with this is I'm going to define an interaction graph for my circuit. So every qubit is going to be a vertex, and every edge between I and J is an entangling gate acting between I and J. And I specify entangling because we've replaced some of the entangling gates with classically controlled gates. So your circuit would start off at some sort of generic graph where each qubit is represented by a vertex, and every edge is a CS gate, or multiple CS gates. Now, every time you apply a dephasing error, remember we can sample it as a maximally mixed state, and the maximally mixed state we can now sample as a 0 or a 1. once you sample a 0 or a 1, every CS gate that acts on it now becomes a classically controlled gate. So there's no entanglement generated anymore. You can apply an S on the neighbors or identity on the neighbors, depending on whether it's a 0 or a 1. So there's still classical correlations in the sense that I've sampled a 0 or a 1 for every error qubit. And depending on what I sample, the different, its neighbors are going to have different circuits acting on them. But there's no entanglement. And this actually lets you, once you sample this, simulate each connected component independently. Each of them represents a quantum circuit that can be classically simulated independently. Now, this is important. I'm essentially taking my circuit using noise to separate out certain vertices. Every time a qubit is hit with noise, it removes all of its edges. And then my graph should split into smaller components. And I'm going to simulate those components independently. Now, the goal is that these components start to get smaller in size if I have enough noise in my circuit. So now, how much noise do I need? This is where we finally see the phase transition in classical simulatability. So for this, we're going to use some tools from graph percolation. These are existing results just in graph theory. These are actually fairly strong for any graph. You don't need to assume anything about the distribution from which your graph comes from. As you have a certain probability that a vertex survives, its edges aren't removed, and it has bounded degree. Delta is the degree. Now, when Q times delta is less than 1, connected components become size O of log n with high probability. So I'm going to sort of pause here for this result. This is an existing result, and the intuition for this is actually kind of, hopefully it's sort of intuitive. If you take any vertex, it has delta neighbors, maximum. And each of those neighbors has a Q probability of surviving. So the expected number of surviving neighbors I'll have at the end of this percolation process is Q times delta. When Q times delta is less than 1, every vertex is very unlikely to be connected to a neighbor. So the chance of finding a very large component is small. You can bound it, and you find that most components are size O of log n with high probability. Now, in our setting, this is sort of a general graph theory result, but it translates very well to our setting. Here, delta is actually bounded by the depth. So each qubit, because is acted on by at most DCS gates. In every layer, I can only apply one gate to for a particular qubit. So, or I can only entanglement with one other neighbor. So each qubit is acted on by at most DCS gates. And at the same time, because I've commuted my noise all the way through my circuit, the qubit survives with an exponentially decaying probability, e to the power minus PD, roughly. This is because D different layers of noise, every time I add a layer, I'm adding more noise, and all of this is commuted to the beginning and built up on the initial qubit. So the phase, just using this, the phase transition will occur when Q times D delta is less than 1. And here you can see you have an exponentially decaying term and a linearly increasing term. This will in depth. So that means there's a constant depth after which this condition is reached. Once this condition is reached, you have connected components of size log n, and therefore you're simulatable in polynomial time. So that might have been a little fast. So I'm going to pause here to sort of like talk. The main message kind of here is that there's this fight between noise and entanglement that's happening in your circuit. As you increase your depth, you're able to entangle different qubits with more qubits. Every layer adds more gates, and each gate can add more correlations. But because of this line here, delta less than or equal to D, you can kind of see that this is bounded linearly in the depth. That is, as every layer can only increase the number of neighbors of each qubit linearly. But at the same time, the noise, because of the commutation, builds up exponentially. So your correlation, your quantum entanglement, your quantum correlations are increasing linearly while your noise is increasing exponentially. So in this fight between noise and entanglement, noise wins, and that's kind of shown in this equation. So just to summarize it, first you sample locations of dephasing errors in the circuit. You initialize a state of the errored qubits to a random bit string. This is the random 0 or 1, because they're all actually mixed once they're errored. Then you can replace every CS gate that acts on an errored qubit with a single qubit gate, which is classically controlled on the sampled bit string. Finally, you can simulate the resulting subcircuits independently, and you can do this using state vector methods or something similar. The point is, these subcircuits get very small, and this becomes tractable in polynomial time. So while we thought it would, if there was no noise, it's expected that these circuits are hard to simulate in polynomial time. The minute you add interspersed noise, these become easy to simulate in polynomial time. So to summarize, noisy IQP circuits are classically simulatable when their depth exceeds a constant threshold. And sort of the main thing you can take away from this, and this is sort of the motivation I was talking about earlier, is that if you want to design some sort of fault tolerance protocol for IQP circuits, you need to leave the IQP framework. And this is something someone was mentioning. You can add non-commuting gates, for example, and that immediately makes it so that the noise doesn't build up. Or you can do adaptive measurement, introduce fresh qubits. These are all different ways of departing from the IQP framework. So the message you should kind of take away is that if you stay in the IQP framework, it's very noise sensitive after a certain depth. And sort of the future directions that I think is sort of interesting is to sort of explore what other families of noisy, shallow circuits are classically simulatable. So two things. I have another slide that I usually do if I have a little bit more time. Let's see. How am I on time?
I think you're doing very well on the time.
Okay.
So,
okay. Cool.
Yeah.
So
yeah. So you could go through it. Yes.
Okay. Cool. There's there's a key question is, how practical is this algorithm? Can you actually use this in polynomial runtime? Is there some hidden constant or anything like that? And the good news is this upper bound on expected runtime, that is this polynomial runtime, actually has no dependence on noise strength. So there's no hidden p to the inverse 1, p to the -1 factor or something like that, where you're going to see a huge constant. If you are past this depth threshold, you will probably be able to run this on a laptop. The bad news is that this depth threshold is very large for practical noise levels. So that's what's actually going to make this hard to practically implement. So for example, I'm establishing a depth threshold after which it's classically simulatable. So if in this example that we just showed, where you have TCS gates and you're doing dephasing with some noise P, if your noise is strength 0.02, for example, then you need to go above a depth of 100 to see classical simulatability. So 0.02 means a 2% chance of seeing a Z error per qubit per layer. And this is actually current practical implementations are probably in the 0.01 range, and their depth is not that high. It's not going up to 300. I believe current depths are around 50. So it's still a little far from the regime where it's practically usable to argue against current supremacy experiments. But it does let you argue against future scalability of quantum supremacy experiments within the IQP framework. And just to sort of hammer this point home, this phase transition that you see from polynomial, we saw after some depth, you see logarithmic size components, even that difference is hard to see unless you go to like a very high number of qubits. And these were some numerics we did just to show, we didn't actually have to simulate every circuit. We can just kind of talk about the size of the subcircuits, and we just plotted the size of the subcircuits. And on the graph on the left, you can see after that critical depth, if you have only 2 to the power 9 qubits, which is a very high number of qubits, the difference between before the phase transition and after the phase transition isn't practically much. This is because of like constant factors in front of your log make it very similar to what it would be if it was a poly-n. So this phase transition is only really something you can see if you go to very high qubits. And then the graph on the right is kind of showing you a similar thing. The purple line shows you the difference between before the depth threshold, every component is of poly-n size. After the depth threshold, the purple line, and below the purple line, every component is of log n. But yeah, you only see the difference practically between the log n and the poly-n if you go to a very high number of qubits. So I'll stop here for questions.
I just wanted to ask about.
Can I start or? Oh, you may go first, Joe.
Yeah. Okay. I mean, just quickly ask, like, for the dependence of the depth you need with the noise parameter. So I'm trying to understand what the noise parameter is. So you need more noise in order to have less depth?
Yes. So
but
this is
isn't that easier to do? Like, I can always have more noise.
So I get, so this is sort of saying like, so I'm saying like the setting is like if you have someone implementing a quantum supremacy experiment and they have dephasing noise of some strength in their circuit, can I classically simulate that IQP circuit? Mm-hmm. If they have a lot of noise, then I'll be able to simulate it at a shorter depth. If they have less noise, then then I can only simulate it after a larger depth.
Yeah, that makes sense. Okay.
Yeah.
You can go, Leandro.
Okay. Yeah, this I don't know. I don't quite remember the results that we have for IQP circuits. I think I'm not sure if it was the first one or not from Michael Bremner.
Yeah.
And I think they say that it's going to be hard to simulate IQP circuits based on, I think, 2 conjectures, one being the collapse of the polynomial hierarchy.
Yeah.
But there's something that feels a little bit weird for me. I'm not sure if it's a lack of understanding, because it feels like if you have a circuit that have a small depth, you could be able in principle to simulate that classically some way. And if you have a larger depth, then perhaps this is going to become harder and harder. And I understand that if you have a lot of errors, then you're basically like destroying your circuit or making like more random. So it's going to be easier. I understand those things, but it feels weird to say that after a certain depth that increases, then it's going to become like simulatable. So I'm not sure if you can expand a little bit on that. If it's just for the noise that you have, it's like what kind of classical simulability are you talking about? Like, could you expand a little bit on that?
Sure. So I'll bring this. I think maybe a useful thing here is I have like this. So yeah, I completely get what you're saying. It is counterintuitive that you increase the depth, you become more simulatable. So really, there is a regime, like you said, that if you have too low of a depth, you won't generate enough entanglement, that you'll probably be simulatable with some sort of, I don't know, MPS or like some sort of, tensor network method. So that's I think the regime you're talking about if you have very low depth. And then there's this in-between regime where I think we think you might see some hardness. And then if you go deep enough, your noise overwhelms your signal. And this is sort of an existing result, right? We already know that if you go past log n depth, then you become completely random, right? So basically, this completely random is very strong, right? Like you go from something. So if you, I don't have a line here, but you can imagine you have a line here where you're classically simulatable because you haven't generated enough entanglement. Your depth is too low. Then you're hard for a while, and then you suddenly become completely random, right? The intuition is that there should be some regime where you're not completely random yet, but you're still very random enough that you've destroyed quantum correlations. And that's basically what we're trying to explore here, is that the randomness is not so random that your output distribution itself is uniform, but it's random enough that you've destroyed quantum entanglement and you're only left with classical correlations. And before this regime, quantum, like you said, you'll be in a regime where you have enough quantum entanglement because of the depth. And then even before that, you would not have generated enough quantum entanglement because your depth would be too low. So does that make sense?
That's interesting because then there's like a sweet spot for constant depth circuits where you can get the most out of them.
Exactly.
And if I understood, this depends on the measurements that you do if you consider interaction graph between the qubits they're using for the circuit, right? Because you showed a graph, interaction graph, and then you showed that you can generate entanglement in it. But if you do like this, if you apply this phase gates, you're going to get smaller graphs, which you can actually simulate. So you're kind of reducing the entanglement.
Yeah.
How can I say, locally, perhaps?
Yeah.
And this allows you to go. So perhaps if we wanted to have a bound on the entanglement that we have, we would need to kind of evaluate very well how many of these nodes can we take out with the phase gates. Do you think that makes sense?
I think I see what you're like. Yeah. Are you saying like you should still be hard? Like if you have somewhere before this omega 1, you would have taken out some phase gates, but you still will have kept the entanglement, right? And you still will have a very connected graph. Yes. Yeah. And that regime, I think, probably is hard, but I think that isn't proven yet. I think it's a very interesting problem. Even there's other results that sort of talk about that. That would be basically, can we find NISC, because we're not doing any error correction here, right? We're not doing, so can you find NISC quantum advantage with an IQP circuit at constant depth?
Yeah.
It's still possible, but it's an open problem. It'd be very interesting to prove it.
Okay, nice. And I know you said that you're going to explore other shallow circuits. Are you thinking about getting out of this IQP and perhaps go to this QNC0 or QAC0? They have been studied like a lot recently.
Yeah.
And try to check what you get from them.
That's sort of the goal. I think QNC and 0 and these might be too general because you could do, I think QNC1, QNC0, you're allowed to do any gate. And here I'm sort of taking advantage of commutation, right? This noise is commuting. So I'd need something where I can get something like commutation. So I think where I'm sort of looking at first is circuits with a lot of Clifford gates and circuits with like random quantum circuits where maybe you can get some approximate commutation type of thing. So yeah, that's what I'm thinking of right now. And those would also be the most relevant for near-term quantum supremacy.
Okay. All right. Thank you.
Yeah, I guess so. We sort of transition naturally to question and answer portion. Anyone else has questions?
Before the slide before your conclusion, the previous slide, you draw the graph, and this one. So basically, you need to locate the place of qubit which has some error. So is this like possible? I mean, usually you need to sample the place of error, right? So
yes, yeah. So So since it's a classical simulation algorithm, I'm not figuring out like I'm given a circuit and given a noise model. So now to simulate the noise, I can do the sampling myself. So I'm not sure I fully understand your question.
So my question is so you already assume you know the noise, otherwise you cannot sample it. So
exactly. Yes, yeah.
So is this is a reasonable is a reason to rule out the hardness of IQP? I mean, you already assume the noise model, but if you don't know exactly their location, probably it's still hard to simulatable. Is it possible?
So I don't need to. So for two things, I guess. One, you can have some noise model in the circuit, as long as some component of it is dephasing. So as long as, for example, say my noise is some complicated poly error and mixed with some unital error, but it has a dephasing component of strength at least p, some 0.1, for example. Then I can now use this whole result to prove that it'll be simulatable after some depth. The second thing is I don't need to know the locations of the so the model is someone else is running a quantum supremacy circuit. I don't need to know the locations of the noise in their circuit. The noise model is stochastic, so I assume I reproduce the same stochasticity on my classical simulation. So I get to sample the noise locations. I'm not trying to figure out where the noise locations are. I choose them randomly because that's the noise model.
Okay, I see. So the whole point is that basically the noise will destroy the entanglement. So without the entanglement, the classical computer can simulate them more easily.
Yes.
And so basically this applied to most error, right? I mean.
So many error models, but it has to have this dephasing component that can commute with the gates. If it doesn't commute, then you don't see the buildup. And if you don't see the buildup, then you don't see the phase transition at constant depth.
Oh, I see. Okay. Okay, cool. And so this is a more general question. So when people say that you are able to simulate the distribution, so this already rule out the supremacy of the circuit. So usually this is based on the hierarchy assumption you mentioned, or there are more like other reasons that you know how to sample the distribution. Basically, your supremacy is gone.
So yeah. So could you say that again? It's yes. If I can sample from the distribution, the supremacy is gone. But those proofs that were based on the polynomial hierarchy, they didn't prove it with noise. All of those proofs are only applied to the noiseless system.
So the reason I ask this question is that because now shadow tomography is kind of classical shadow tomography is kind of popular now.
Yeah.
And so basically, and also they mentioned they can simulate the outcome of the circuit. I mean, basically the expectation of observables you want, but this seems still leave room for supremacy of the circuit. I'm not sure. Yeah. Anyway, I just wonder what's the community thinking. You just try to attack the distribution, or you try to attack the circuit itself. Usually, what's the attacking point? Probably it's not very clear question. Okay.
Yeah, I'm not sure I fully understand, but yeah. I'm also not very familiar with shadow tomography as well and how it relates to sampling. But yeah, it is very popular these days.
Okay, thank you.
Okay. Okay, I just wanted to ask something about. So yeah, you were saying that like the belief that we have that like the IQP circuit sampling is hard, is like doesn't have the noise. I was wondering, like, is this sort of the intuition where like you have some problem that's hard if you wanted to do it exactly, but gets easier if you were willing to do it approximately? But probably it's not the same intuition, right?
It is a similar thing, but yeah, it would be a different technique. So that's saying like, yeah, exact sampling is hard, maybe approximate sampling is easy. But this is a little bit different because approximate sampling is also thought to be hard. Yeah. So this is saying you now introduce noise in your circuit. So it's a little bit different than that. It's basically saying a very perturbed version of the circuit is going to be easy, right? Because you're perturbing at every layer. So it's not just it'll be far from it won't be an approximate to the noisy distribution will probably not approximate the exact distribution. The hope was that the noisy distribution itself would be hard to simulate from, but we're basically showing that this is not true.
Okay, yeah, maybe just one final question. Like you made a comment earlier that, I mean, you weren't going to discuss it, but I just wanted like some brief comments about like verifying.
Yeah.
Like, because you said that there's also still the issue of verifying whether your simulation, I guess, is correct, right?
Yeah. So yeah, this is something I don't have a lot of expertise in, but like this is all like very nice, but like as you scale to higher qubits, besides the problem of it possibly not being hard, the extra problem is that your quantum computer spits out something and you have no way to know if that was even the right thing. So there's different ways of trying to verify it. People sometimes introduce like a trapdoor. There's been stuff about another reason why IQP circuits are recently popular is because there's been some ideas to insert some secret into the IQP circuit, and then something that allows it to be classically simulatable if you know the secret. So that way, an untrusted quantum computer runs the circuit, and basically you can verify it because of some sort of some cryptographic assumption. So there's like these very like it's a sort of you have an untrusted quantum computer and you want to make sure that it's doing something that a classical computer could not do. I'm probably not explaining this very well, but yeah, I feel like there's a completely different set of proof techniques, stuff used for verification. Just out of the box sampling is probably not going to be efficiently verifiable. All of the verification techniques, cross entropy benchmarking and everything like that scales exponentially. So they're not going to be scalably verifiable.
Okay, yeah, okay, thanks. Yeah, so if there's
perhaps
okay,
one last thing. Yeah, I'm not sure if I forgot, Joe, but you mentioned that you don't use anti-concentration, but I think right now I don't remember, what do you use to obtain the result? So like, is there assumptions like
it's very general. The only assumption is that your gates are O of 1 local. I think I might have a slide which goes through the thing. So you cannot have like every gate is K local basically. And then you have to assume that your noise is of this form, that is, it has a dephasing component.
Yeah.
And those are your only two assumptions.
No, I'm not sure how to phrase it. It's because I'm used to the other way around. So you perhaps get a problem, or you have like some conjecture, and then you show that if there's Like if you have, for example, a classical circuit that is going to simulate it, then you're going to break this down, or you show that your classical circuit cannot output the output of the quantum circuit with a certain probability. So I guess what I'm asking is, you have these assumptions and you have your noise, and then you're going to use some percolation tools to evaluate the balance between the depth and the noise that is happening. But I feel that I missed perhaps a last part saying that, okay, now for sure it's going to be easy because of that.
Oh, I see. So maybe, I guess I did kind of go through that. So
yeah, I think you did. I think I forgot.
I went through too quickly. You're right. I should probably explain that. So basically, I said this at the end. So simulate the resulting subcircuits independently using state vector methods or similar. So once your subcircuits become O of log n size, each of them is simulatable with the state vector method in polynomial time independently. And basically, so you simulate each of these subcircuits independently using state vector methods. Everything's in polynomial time. And I guess the thing I should have written here is that this distribution that you end up with after doing this whole sampling thing is an exact sampling of the true quantum circuit, the true noise circuit. It exactly samples from
an exact sample. Okay.
Yeah.
Okay. Well, so yeah, okay. Thank you. I think that's it then.
Cool.
Yeah.